Okay, picture this. A perfect vacuum. I mean, truly, absolutely empty space. Now, what if I told you that inside this perfect void, a real, measurable force can just appear out of absolutely nothing? It sounds like something straight out of sci-fi, but it's a very real phenomenon called the Casimir Effect, and honestly, it completely messes with our idea of what empty even means. So let me ask you this directly. You take two metal plates, they have zero charge, and you stick them in a perfect vacuum. Should they attract each other? I mean, it sounds impossible, right? All of classical physics would scream, no way. Two uncharged things in a void should just float there, totally ignoring each other. But, the quantum world, it has a much, much weirder answer for us. And yeah, the answer is yes, they attract. This is the Casimir effect. It's a force that doesn't come from charge, it doesn't come from mass, it comes from the very fabric of the quantum vacuum itself, just because you put some boundaries in it. So how on earth does that even work? All right, so the standard explanation, the one you'll find in the textbooks, comes from quantum field theory. And it really boils down to counting all the different possibilities that are constantly simmering inside of so-called empty space. Let's break that down. So first things first, you got to throw out the idea of a truly empty vacuum. Quantum mechanics tells us it's this bubbling sea of virtual particles. You can think of them as waves of every single possible length just constantly popping into and out of existence. Now, here's the key. When you stick two metal plates in there, they act like mirrors, and they create a boundary. They fundamentally change the rules about which of these waves are allowed to exist in the space between them. And this leads to a really cool concept, quantization. See, between the plates, only the waves that fit perfectly, kind of like a standing wave on a guitar string, are allowed to be there. The wave modes that are permitted are dictated by this formula, which depends on A, the distance between the plates. If a wave doesn't fit just right, it's just not allowed in. Simple as that. And this, right here, this is the heart of the whole thing. Outside the plates, you have this continuous infinity of all possible waves. To get their total energy, we use a tool from calculus called an integral. But inside the plates, it's a whole different story. You have this restricted, discrete set of waves, and their energy gets calculated with a simple sum. So here's the mind-bending part. The energy outside is infinite, and the energy inside is also infinite. But, and this is the magic trick, through a mathematical process called regularization, physicists can meaningfully subtract the inside infinity from the outside one, and what you're left with is a small, finite, and negative energy. A lower energy state between the plates means there's more pressure on the outside, pushing them together. And boom, that's your attractive force. The really crucial thing is that all of this leads to a precise, testable formula. The force for a given area depends on fundamental constants we all know, like Planck's constant and the speed of light. But, most importantly, look at the A in the denominator. The force is inversely proportional to the distance A raised to the fourth power. That 1 over a to the fourth scaling, that is the classic unmistakable fingerprint of the Casimir effect. But what if that whole story of virtual particles and subtracting infinities is just one interpretation? There's an alternative model out there that proposes a completely different picture. One where reality isn't a continuous field at all, but a discrete computational grid made of these tiny, fundamental building blocks. This quote really frames the new perspective beautifully. In this alternative model, which is sometimes called the Gibsonian model, the force doesn't come from vacuum waves. Instead, think of it as a kind of information pressure. The plates aren't restricting waves, they're restricting the number of ways that information can flow through a fundamental grid, and that creates a pressure difference. And here's how you can see the translation. The familiar Hasse constant from the standard formula, well, it gets replaced. In its place, we have new characters, psi, which represents a fundamental unit of information or a token, and c star, the speed at which that information zips across the lattice. The physics ends up looking similar on the surface, but the engine underneath is totally different. So in this view of the universe, space is this dynamic network of tetrahedra. All of physics, everything, emerges from simple, local rules that govern how a fundamental piece of information, called a tetrix, can move from one point to its neighbor. It's a way of building reality from the ground up, without ever needing to start with a coordinate system. Now look, a new model is interesting, it's cool to think about, but is it science? Well, to be science, it has to make a unique, testable prediction. And this one actually does. It offers a falsifiable fingerprint that could, in theory, separate it from the standard model. The key idea here is that this tetrahedral grid isn't perfect. It has tiny defects. The model suggests there's a mechanism it calls orbit repair, where at really, really small scales, the lattice can actually fix these defects. And in doing so, it slightly changes its own effective properties, things like its stiffness or how easily information can flow through it. And that physical change, that self-repairing, translates directly into the math. The model's fundamental constant, that CC star thing, isn't actually constant after all. In the regions where this orbit repair is happening, it gets a tiny little correction factor, which we're just going to call epsilon. And here it is. This is the kicker. The model doesn't just say, oh, there's a correction. It actually calculates a specific value for it. Epsilon is predicted to be just about 1 divided by 1656. This is the concrete, numerical prediction that we can actually go out into the real world and look for. Okay, so let's be super clear about what this means. This is not predicting some new force law like a 1 over a to the 5th power or something. No, it's predicting that the standard 1 over a to the 4th Casimir force is just a tiny, tiny bit stronger than mainstream physics expects, about 0.06% stronger, and only at the very small scales where this lattice repair stuff would kick in. 0.06%. I mean, that is an incredibly small signal to find. So how could an experiment ever possibly hope to pull out such a tiny effect from all the real-world noise and experimental messiness? Well, measuring the Casimir force is notoriously hard. You have to deal with the fact that your plates aren't perfect mirrors, their surfaces are never perfectly smooth, there's always some heat creating its own pressure, and you get these tiny electrostatic dirty patches that create their own forces. All of these effects are way, way bigger than the tiny 0.06% signal we're trying to find. But here's the really clever part. The prediction isn't just for a constant offset. It's for a signature that should turn on at a specific, very small distance. So you wouldn't be looking for a force that's always 0.06% off. You'd be looking for a distinct kink in your data plot, a little step-like change that only shows up when the plates get close enough to start probing this hypothetical lattice repair mechanism. So this suggests a really clear strategy. First, you do the absolute best, most precise Casimir experiment you possibly can. Then, you use standard theory to model and subtract all of those known errors, the big four we just talked about. And finally, you look at what's left over, the residual noise, and you search specifically for that characteristic kink. If it's there, and if its size matches that 1 in 1656 prediction, you might have just found brand new physics. And that just leaves us with this incredible thought. The Casimir effect is a cornerstone of modern physics. It's our direct window into the quantum vacuum. But what if, hidden within its precise measurements, a tiny deviation, less than 0.1%, is the first clue that everything we see, our entire reality, is actually running on some kind of hidden computational grid? That's the huge question this hunt in the noise is ultimately trying to answer.